Here we go. A spacecraft has a mass of 3.25 times 10 to the fourth kilograms. Its engine can exert a thrust force of 7.25 times 10 to the fourth newtons. At what rate will the spacecraft accelerate? Ooh. Josh, what's this question asking me to find in part A? You know what? Let's fall back on our tried and true method because I'm not quite sure where to go, Josh. I'm going to go A equals question mark because I've written some down and I feel better. We have a whole bunch of equations with acceleration in them, but what did they give me right here? What's this number telling me? Loud and proud, you're right. And what's this number telling me? I'm going to use the acceleration equation that has F and M in it. F equals what? Get the A by itself, please. I'll give you a hint. A equals. Yeah. F over M. I took a tiny bit of a shortcut here. I didn't actually write F equals 7.25 times 10 to the fourth, and I didn't actually write M equals 3.25. We're taking a little bit of shortcuts as we're getting better, but I still used the DFIC method. I just kind of did some of it up here. So the force is going to be 7.25 times 10 to the fourth. The mass is going to be 3.25 times 10 to the fourth. I did a check. The units are newtons and kilograms, which are my preferred units. What do you get? Crunch this. And I would strongly encourage all of you during today's lesson to be crunching these numbers on your calculator. We're going to, in a few days, be getting pretty complicated on calculators. And so it's nice if you can do the simple stuff so I can build on the more complicated stuff. Josh, what'd you get? Can't be right. It's got to be 2 point something because this is roughly 7 divided by 3. 2.32? 2.23? Rounded off properly? Yes? Is it 2.23? Anybody up? 2.23? Okay. If you didn't get that, try and figure it out. If you still can't get it, call me later. I'm going to write 2.23. It's an acceleration, folks. Units? Meters per second squared. Keep that on your calculator. Get it okay this time, Josh? Typo, right? Let's keep going, Josh. Let's read along part B. It says, if the spacecraft maintains this constant acceleration for 12 minutes, I don't like minutes, but I can fix that, before turning off the engine. I noticed they underlined turning off the engine, so I'll pay attention to that. And if its initial velocity was 5.6 times 10 to the third meters per second, what's B asking me to find? VF? Hey, this is kind of like familiar from way before Christmas. This is good review. So I'm going to go VF equals question mark. What's that 5.6 times 10 to the third? Oh, we're in pretty familiar territory, I think, yes? What's that 12? Why don't I like it? Hours? What's our preferred units for time, folks? Seconds. It may feel like my class takes hours, but believe me, my class goes by in seconds, my friend. So I'm going to write T equals 12 minutes. Whenever I don't like the units, I'll put them in. How do I convert minutes to seconds? It's probably going to be something to do with a 60. Times or is it divide? Can I give you a good trick? I've never memorized it. I always go with 1 minute because I know the answer. 1 minute is how many seconds exactly? To turn a 1 into a 60, would you divide by 60 or times by 60? So 2 minutes is 120 seconds. You times by 60. So for 12, we would go times by 60. If you wanted to, you could build the whole unit chain that I taught you before Christmas, and the units cancel, but I'm giving you now shortcuts. 720, yes? Is that correct, I hope? Well, a bit of a problem, Josh. I know VI, I know time. That's 2 things. I need 3 things to find the fourth, and I only know 2. Or do I? Now, folks, I would have no problem giving you this question on the test, but not asking you part A as a hint first, going straight to part B, and Ethan expecting you to clue in, oh, I can get A because he gave me a force and a mass. Is that fair game? Okay. So I know A, it's sitting right there. So which equation would I use, Josh, if I have VF and I know VI, T, and A? Some of you might even have memorized that still. So now it's plug and chug. 5.6 times 10 to the 3 plus, I'm going to write 2.23. Can I ask all of you, use your answer button there. It's less typing and it's more accurate. So if you still have that 2.23 stored. Now if you went 12 times 60, then you've cleared it off and you'll have to use 2.23. And time is 720. This is a guess. You're going to get a fairly big number, probably in the thousands, I think. If I'm doing some really quick math in my head, I think something in the 7,000, 8,000 range. Sahara, what'd you get? Which one of those is correct? 7,205 or 7,206? I'm going to go to 3 sig figs, so I'm going to write 7,210. But keep that on your calculator. Okay. C. Ooh. What's C asking me to find? And I'm doing this also because after Christmas, I'm jogging the memory. I'm brushing the cobwebs off your brain. This is stuff that we could do kind of in our sleep before Christmas. McKenna, what's C asking me to find? Which equation? By the way, I'm not going to relist everything. I could, but I got VI there, I got T there, I got VF there. A is, it's all right in front of me, so I'm not going to make you necessarily relist everything. You can if you really find that helps, feel free, but I'm now saying you can probably take some shortcuts. Which one? I got a bunch of options. I looked at VF squared equals VI squared plus 2AD, and I looked at D equals VIT plus a half AT squared. I noticed that both of them need A. So I'm going to have to use a calculated value no matter what. I can't avoid that. So I wimped out and I used the one that had the D by itself already. I went for easier, less work. VIT plus a half AT squared. VI, 5.6 times 10 to the third. T, 720, plus 0.5, 2.23, 720 squared. We're going pretty fast. We're going 5.6 times 10 to the third meters per second. That's 5.6 kilometers a second. And we're traveling for 720 seconds. You're probably going to get a fairly big answer, I suspect. Ethan, what'd you get? I don't want to write that much, so I'm going to go 4.61 times 10 to the what? You didn't get 4.61? What'd you get? $5.32 times 10 to the... That can't be 5 million then. What'd you get, Ange? Yeah, by the way, I think Ethan is correct. I think Ethan is correct. So you want to double check. Now, what are common mistakes? Did you put the squared on? You did? And you put a 0.5 there? What'd you get? Same as Ethan. Yeah, Ethan, tell me what you got again. 4 point. Is it 10 to the 6th? I can't remember. The 4.61 twigged my memory from this morning. I couldn't remember the rest of it. Is that fast? Pretty fast. Well, you know what? This is how outer space works. If you accelerate, you'll just continue to speed up, 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 speed up. Eventually, you'll be going fast enough that all that weird relativity stuff kicks in, and then it doesn't follow this physics anymore. We have to bring in all the Einstein equations. But the speed of light was 3 times 10 to the 8th. This is 10 to the 6th. We're nowhere near that, so we're still good. Okay. D. What will the velocity of the spacecraft be after 48 minutes, or 60 days, or 4 years? What's the answer? Yeah, Ange? Oh, units are wrong. Is that what you're saying? Duh. Come back from Mexico, Mr. Dueck. Thank you. Let's go back to D now. Yeah. No. Oh, sorry, what? What's loud? Mark, you just impressed me, and that isn't that easy to do. Say it again, what? Why is the answer the same as our answer from B? And we shut off the engines, and then Newton's first kicks in. We keep going in a straight line at a steady speed. That's how outer space works. And that's a tough one for you to wrap your brain around. My last class could not, I'm impressed. My last class could not come up with the idea that once we shut our engines off, we coast. They went, first of all, they tried calculating this. They hadn't noticed we shut the engines off. And then I went back here and I said, hey, we underlined this, turning off the engine. And then they said, oh, 0? You're used to, on the Earth, everything coming to a stop. But that's because, Ethan, when you're coming to a stop, there's an unbalanced force acting on you, usually friction or air resistance. None of that in outer space. Space travel, once you get into space, is easy. We have to spend the vast majority of our fuel getting off the Earth. We say you have to leave the Earth's gravity well. We imagine that Earth's gravity is like a well, and you got to climb your way out of it. But once you're out there, you're coasting most of the time. When we sent our New Horizons probe to Pluto, we had to get it off the Earth and get it going really fast, but then it coasts. Our Voyager probes, we have 2 of them. They've left the solar system. They're coasting. They're going to keep going forever, unless alien intelligent life finds them. I imagine then they'll grab them and bring them to a stop. Or if a few thousand light years from now, they run into some other gravity well from some other object like a star or a planet that happens to be in their path. Otherwise, Newton's first, baby. Straight line, steady speed. Well done. Look at the rest of the people here and just shake your head in pity. You can if you want to. You can just do the... Now, let's get to today's lesson. That was all review. Free body diagrams, which I'll often abbreviate as FBD. A free body diagram is a picture that represents the object that you're analyzing with a small dot. Any forces acting on the object are represented with arrows, roughly to scale if possible. What do I mean by roughly to scale? If you know that the forces are balanced because it's not accelerating, try and draw the arrows roughly the same length. If you know that one force is bigger than another object, try and make the arrow bigger than the other force. That's what I mean by roughly to scale. We're going to use Newton's laws to figure out what forces are missing and what forces are acting on the object. Example 2 says this. Free body diagrams for 4 situations are shown below. I should be technical. Technically, these aren't free body diagrams because they didn't represent the mass with a little dot. But the concept is still good. It says the net force is known for each situation right down here, but the magnitudes of a few of the individual forces are not known. Analyze each situation using Newton's laws and determine the magnitude of the unknown forces. This seems really complicated. It's not. Caleb, see this picture right here? What does it say that the net force is exactly as a number? So that means since the net force is 0, that the forces must be, I'm looking for a word that begins letter B. This picture is not balanced right now. If I'm pulling with 50 newtons to the right, how big must force A to the left be exactly as a number? Yes. And if we're pulling 200 newtons down, but the net force is 0, how big must B be exactly as a number? So a free body diagram If you know the net force, you can figure out missing forces, or if you don't know the net force, you can figure it out from the free body diagram. Grace, look at the second picture. It says the net force is 900 newtons up. How big must C be? And I'll give you a hint. It's not 900. It's got to be 1100 newtons. Has to be. How did you get that? Really what you're doing is you're going 1100 minus 200 equals 900. You're doing some vector mathematics, and we'll get into it way more in Physics 12, but in Physics 11 I want to kind of do it intuitively. Cool. Amy, what's the net force here? Magnitude and direction. Which way? Is there any net force up and down? I don't know. So the net force up and down must be 0. So how big must E be if I have that up there? How big must E be? Has to be exactly 300. Those two happen to be canceling each other out. Okay, how big must D be if my net force is 60 left? How big do I have going right now? I want that to be 60 left, so how big must I be pointing to the... Sorry, I said how big do I have going to the left right now? 80. What goes there so that I end up with 60 left? 140? Disagree. 20. Is that right? 80 that way and 20 that way, that's the same as 60 that way. That's the net force. What we mean by the net force is the vector combined sum of all the forces, replacing them just with one. So this idea of a free body diagram, really handy to figure stuff out. Isabella, what's the net force, magnitude, and direction on this one? So how big must G be? Yep, 50 is correct. And then Isabella, do we have a net force up or down? Which means it's 0. So how big must force H be compared to force F? If it was 0, that can't be the case. How big must force H be? If force H is 80, how big is force F? How big must force H be compared to force F? Exactly the... Now, why is that important? There will be questions where I might ask you to find force F, and you can't. But you can find force H. Well, then you find that, and you know it's got to be the same answer. See how we're going to be clever that way. There's going to be times when we can't find the force that we want, but we'll say, oh, look, there's another force the same size. Go find that one. I'd like you to look at a book at rest on a tabletop. You know what? Your binders. What would a free body diagram for this look like? So now let's do a true free body diagram. Let's represent the book with a dot. I'm going to strongly, to the power of infinity, strongly, Alex, encourage you when you're doing your free body diagrams to go systematically. And what I mean by that is kids always want to put the toughest force or the force that you're being asked to find on the diagram first. Do not. So you're going to hear me say a phrase over and over, and it starts today. I'm going to say this. What are the forces acting on this book? Get the obvious one. And what I mean by the obvious one, all of you lift your feet off the ground right now. Which force are you feeling tug you down? That's the obvious one. Which force is that? Everybody draw an arrow pointing down, and let's call it FG for gravity. I always start systematically getting the obvious ones. Often once you've filled in the obvious ones, the tricky one will become obvious because you've got more arrows to work with. Look at your binder. Is it sinking into the table like quicksand? Is it flying off the table like Superman? Is it accelerating at all? No, that means the forces must be, I'm looking for a word that begins with the letter B, Paige, balanced. Look at my picture. Those are not balanced. What must I draw an arrow pointing which way? I don't know what that means. Can you give me the word, Isabella? The arrow that I draw pointing up, is it going to be bigger, smaller, or the same size as mg? It's got to be the same size. Eyeball it. For me, it's about like that. And call that Ft for table. Those are the two forces that are acting on the binder if it's sitting by itself and if you're not leaning on it like Paige is, adding an extra force. So looking, for example, at Connor's binder right there, I'm telling you right now, gravity's pulling it down and the table is pushing it up and the net force is 0, which is why it's not accelerating, it's staying at rest. Another good example is when we have a mass hanging from a rope. So this says draw a free body diagram for the following masses that are just dangling for the rope. We have one situation at rest and one where it's accelerating. Let's do the one at rest first. Let's represent it with a dot. What are the forces acting on this? Get the obvious one. Gravity. Fg. Is this mass accelerating downwards according to this question? Is it accelerating upwards according to this question? In fact, it says it's at rest, so what is the acceleration as a number exactly, Matt? No, that couldn't be at rest. That would be in free fall. It says it's at rest, so what is the acceleration exactly in your head as a number, Matt? So what's the net force as a number exactly? So my forces must be, I'm looking for a word that begins letter B. Are you seeing why Newton's first is so handy? It really is handy. So which way am I going to draw an arrow? Bigger, smaller, or the same size as mg? What arrow is that? It's the rope. We're not going to call it rope. We're going to use a special force. The name that we give to the force exerted by a rope or a cable or a line is tension. Capital T for tension. Will the right-hand diagram be the same? Let's find out. On this right-hand situation, it wants us to draw a free body diagram. Kai, what are the forces acting on this object? Get the obvious one. Which way is this object accelerating? I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Which way do I have an unbalanced force? Which way am I going to draw a longer arrow? All three are the same question because of how Newton's first works. I always exaggerate it so it catches my eye. When I look at that diagram, I know it's accelerating up. What force is that? It's the rope. What was the special name that we just gave to the force from a rope? It's what you're feeling right now? Yes. By the way, where is the rope more likely to break? The left-hand diagram or the right-hand diagram? Why is the right-hand diagram more likely to break? Tension's bigger. Look at it, it's bigger than mg. And that might be kind of a Captain Obvious, yeah, the rope's more likely to break when I yank up on it, but I like the fact that this confirms the Captain Obvious physics that we know the answer for. It suggests we're doing this right. Next page. We're going to be looking at different types of forces over the next few days. I've just kind of snuck tension in to you. But one of the forces that you're most acquainted with is the force of gravity. Recall earlier today in last class, I had you all lift your feet off the ground and you suddenly went, oh yeah, gravity's pulling me down into the chair. I can feel it. It's always there, but you kind of take it for granted. Gravity is the force that the Earth's mass exerts upon you. The force of gravity is calculated as follows. We start out with Ayla, F equals what? We think F equals ma. Don't write that down. I say A is the acceleration due to gravity, so I put a lowercase g there. And I did give you that formula on your formula sheet, but you'll probably end up memorizing this one because it's such a subtle derivative of F equals ma. F equals what? What's another word for the force of gravity? No now. Weight. No now. Wait. Another word for the force of gravity is weight, and this is important. I will ask you this on a test. Weight is measured in newtons. It's a force. It's not measured in kilograms. So example 3 says, find the weight of a 35 kilogram object A on the Earth and B on the moon. You know what? Let's go like this. A right there. Let's draw a line down the middle, and let's put B right there. What does this want me to find? Armand, what does this want me to find? You said the word "the," spoiling my punchline. You're correct. If you had just said weight, I was going to say no now. Yeah, it wants me to find the weight, the force of gravity. So I'm going to start out by writing Fg equals mg. And over here, I'm also going to write Fg equals mg. Mr. Dueck, won't those both give us the same answer? Look up, look up, look up, look up, look up. I'm going to put a little e here for the acceleration due to gravity on the Earth. I'm going to put a little m there for the acceleration due to gravity on the moon. And I want you to notice your mass, the mass does not change. The mass of a 35 kilogram object is the same on the Earth and on the moon. What's going to be different? The weight, the force of gravity. So let's crunch the numbers here. We're going to get Fg equals 35 times 9.8. I can do that in my head. It's going to be 350 take away 7. 343, double check me. Or am I wrong? I could be wrong. 343? Am I right? Give me some feedback, people. Now, what does that mean? McKenna, it means if you're lifting a 35 kilogram mass up, you are exerting 343 newtons of force through your arms against gravity. On the moon, however, it would be 35 times... Oh, what did this question, Armand, tell me that G was on the moon? Yep. I can do that in my head, too. It's going to be 35 plus 7 plus 7 plus 7. It's going to be 35 plus 21. 56, double check me, but I think so. Units, it's a force. Okay. Has this object's mass changed on the moon? No. What has changed? Its weight. And so on the moon, if you were lifting this 35 kilogram object up, you would only have to exert 56 newtons of force against the moon's gravity. You see the key difference between mass and weight? Weight is a force. It's planet dependent. It changes from planet to planet to planet. Did the mass change from planet to planet? No, no. This is how we're going to solve everything, Physics 11 and Physics 12. Here it is, the focal point of the lesson. To solve any situation involving forces, we're going to use a tug-of-war analogy. Who has Mr. Kamosi for math right now? You guys are just doing systems of equations, yes? There is a way to teach this using systems of equations, and when I first started teaching, that's how I taught it. And then I stole the tug-of-war analogy from my friend who teaches at SRT. Got to give him full credit. So what's the tug-of-war analogy? We're first of all going to draw a free body diagram, labeling all the forces and using our knowledge of Newton's laws to figure out any that are missing. And then we're going to use our knowledge of physics to decide which of all those forces is the winning or strongest force. And then here is the equation. No, you cannot put this on your green sheet. You're going to have to commit it to memory. This is our template that we're going to use to derive every other equation. We're going to go like this. Winner minus loser equals F net. We're going to imagine on our free body diagram, Ange, that the forces are having a tug of war, but one of them is winning, one of them is losing, and when you combine them, that's your net force. Oh, except I'm going to be even more specific. If you look on your green formula sheet, I didn't actually write F equals MA. I wrote F what equals MA. So where F net is equal to what, MA. So now we're going to put it all together. Example 4 is a little easy. I like it, but it's a little easy. But we're going to start here. It says this: suppose the box is resting on ice and the following forces are acting on it. Looks like I got a 6, looks like I got a 14. A says add any forces that you think are missing. You know what? This is a job for a free body diagram. I'm going to represent the object with a dot. What are the forces acting on this box? Get the obvious one. Pardon me? Good. I'm going to write mg instead of fg. I typically just write the equation. Excuse me. Is this box sinking into the ice like quicksand? Is it flying off of the ice like Superman? Then in the vertical direction, it's not accelerating. The forces must be, I'm looking forward, that begins letter B. This diagram is wrong. I must draw an arrow pointing which way? How big? Bigger, smaller, or the same size as mg? Eyeball it. What's that? The ice pushing up. Those were two that the diagram was missing. Now the diagram also has a 14 Newton force to the right and a 6 Newton force to the left. There is the free body diagram. That has all of the forces that are acting on it. B. Kyle, what does B want me to find? Keep going. So what does it want me to find? Yes. Okay. Did they give me a VI, a VF, a top? No, we're in forces now. You know what? Look at your free body diagram. In the vertical direction, we're not accelerating at all. In the horizontal direction, who's winning? Who's losing? What's winner minus loser going to equal? MA. So you ready? Our equation for this specific situation, winner minus loser equals MA. Don't memorize that because that equation will change for every different situation. What did we want to find, Kyle? How would I get the A by itself? I'm feeling lazy. Everybody look up. Cross that out. Tuck that there. We can do that on the same line, can we not? So it seems to me, Kyle, that the acceleration is going to be 14, take away 6, divided by, what's the mass? I'll either give it to you written in the question. Actually, most of the time, I'll stick it on the picture. So I'm reusing a lot of these. Which is what? I can do this in my head. It's 8 divided by 3. I think you're going to get 2.66666666666666. Yeah. Yep. But then what did I say F net was the same as? Yep. Good question. 2.67, yes? If I go to 3 sig figs? That's the magnitude. If they had asked for a direction, I'm not sure, because how fast will accelerate is kind of vague. Which way must this be accelerating, to the left or to the right? Which way must this be accelerating, to the left or to the right? Why must it be accelerating to the right? That's the unbalanced force, Newton's first. Example 5. Suppose the box below is sitting on a table and accelerating to the left. A says add any forces you think are missing. That's code. This is a job for a free body diagram. So I'll do my free body diagram. How about right over here? What are the forces acting on this box? Get the obvious one. Get the obvious one. Get the obvious one. Somebody say it. Thank you. Apparently not so obvious. Is the box sinking into the table like quicksand? Is it flying to you like Superman? By the way, we will eventually be doing questions where things are sinking or flying into the air, and it'll be a fairly simple tweak if we do good free body diagrams. But for now, I think I can say the table is pushing up with the same force as gravity. I notice I have Billy pointing to the right. I'll call Billy's force FB for Billy. I have Abe pointing to the left. Am I going to draw Abe bigger, smaller, or the same size as Billy's 24? How do I know bigger? And that's which way the bigger unbalanced winner force must be, Newton's first. Starting to see why I said Newton's first is really a handy law to do free body diagrams with. I'll exaggerate it, Mila, so it catches my eye. Here is F Abe, and I'll even put an equals question mark. Cool. B wants me to find F Abe. Okay. Who's winning? In the vertical direction, who's winning? No one, it's a tie. In the horizontal direction, who's winning? Who's the loser? Indiana, you didn't see. I said, who's the loser? And she looked at you. Oh. Oh. Bonson Park, 3 o'clock. If I'm not there, you two just start without me. Oh. Who's the losing force? So we have winner minus loser. And Mila, what does winner minus loser always equal? F net, which is MA, so we'll go straight to that. By the way, I want you to notice what we've actually done. Before Christmas, we always let to the left be negative. Here, we've said, you know what? It's easier to let that be positive. And in this unit, we're going to decide positive is what makes the math nicer. We'll sometimes let down be positive because it makes the math nicer. We'll sometimes let up be positive. We'll sometimes let right be positive. We'll sometimes let left be positive. We're going to say who's winning. That makes the math cleaner. Oh, Mila, what's this question asking me to find? How would I get the FA by itself? Okay, plus what? What? Loud and proud. Oh, plus the FB over? Does that make sense? Yes, to get the FA? Look up, everybody. I'm going to do that. Now, if you feel, and you just have to go plus FB, and then draw the, like if you have to do that because that's how you do it in math equation solving, go ahead. I'm not going to prevent you from doing that, but I'm really trying to get you comfortable with moving stuff from side to side. And I hope you're finding in your math courses, looking at the parabola and rewriting equations for systems of equations, I hope, Connor, you're finding, oh, it's actually just formula manipulation, and I can do a lot of it in my head and know that I'm doing it right. I'm hopeful that this is kind of spilling over. Ethan's nodding his head. Good. Kyle, let's finish this, you and I. So FA is going to be, Kyle, what's the mass? Look at the picture. Look at the picture. Yeah, uh-huh. What's the acceleration? They told me. Yep. Should that be negative, Mr.? No. I know it's to the left, but we've decided for this question that it's nicer to make that positive. Plus, what's FB? I can do that in my head. That's going to be 16 plus 20. 40 even, I think? Units, Kyle. It's a force. Yep. This is the power of a free body diagram combined with winner minus loser equals MA. I like example 6. I like example 6. Example 6 is a nice question. We're going to finish with example 6, and then I'm going to continue this lesson next class because I really want to give you about 15 minutes or so to work on the homework from last day. Here we go. Ayla, what does example 6 want me to find? Tension, like you're feeling right now. You know what this is a good job for? A free body diagram. How do I know that, by the way? Eventually, you'll realize there's multiple forces in this question and in an acceleration. That's when you really should do a free body diagram. Sometimes kids will try and memorize certain situations. I would discourage that. The amount of effort, you'll find a free body diagram when you get good at it, William, takes about a second. And the amount of value you get from that well outweighs that 1 second of time. So I am, Ayla, going to represent the mass with a dot. What are the forces acting on it? Get the obvious one. Yep. What else? I know there must be another force acting on this, and the reason I know there must be another force acting on this is because if there was no other force acting on this, if that was the only force, what would this acceleration be as a number exactly? And what direction would it be? Down at 9.8, because it'd be in free fall. Which way are we accelerating according to this question? Loud and proud. Which way am I going to have a bigger arrow, unbalanced force pointing? Same answer. What force is that? It's the rope, but what did we give the special fancy schmancy rope name force? What you're trying to find. Those are the forces acting on it. Who's winning? Who's the loser? Oh, Connor! You didn't. I said, who's the loser? And she looked at you. Oh. Boy, you people aren't nice to each other at all. Who's losing? So minus gravity. Mila, what does winner minus loser always equal? What? By the way, you can also see, Ayla, I could have given you the tension and said find the acceleration. How would you get the A by itself? Divide by M. But here, I want you to find the, how would you get the T by itself? Do you mind if I go? I think that's clear work, is it not? I think. So tension is going to be M 12 A 2 plus M 12 G 9.8. Mr. Dueck, doesn't it need to be negative 9 point? No, I took care of the negatives and the positives with my winner minus loser shtick. In fact, if you want to know where the negative in front of the 9.8 was, it's sitting right there in that equation, right on that line right there with the minus sign. Do that one in your head, Mr. Well, maybe. It's going to be 120 take away 2.4. It's going to be 117.6 plus 24. 137 points, 141.6, he says, maybe? I calculated that. It was 141.6, is that what I said? Mila, I go, first of all, can you see the 24? Remember that. I go 12 times 10, not 9.8. Which is 120. Then I subtract 0.2 times 12. 2 times 12 is 24. 0.2 times 12 is 2.4. So I went to 120 minus 2.4, which I can do in my head, plus 24, which I can do in my head. That's how I did it. For the next 15 minutes, you can continue to work on the homework from last day. There are some questions on the homework from last day that I didn't give you the answers for. I'll go over those answers when I see you all on Monday. Kai, look like a bunny.